Good morning, ladies and gentlemen. Welcome to Sequences and Recurrence Relations. A sequence is essentially like a set of dominoes. If you know the first one, and if you know how they fall, then you can knock them all over. So, a typical sequence might look like this below. 2, 5, 8, 11, 14. Now that sequence is obviously just adding 3 on. We know that this one here is the first term. Nice and easy. Second term, etc., third, fourth, fifth, until we get some distance out here where we don't actually know the number is, but we call that the nth term. Now, if we want to refer to the one before the nth term, we do the n take 1th term. That's here. N plus 1 is there. Now, for terminology, this, if it's the first term, will be called T0. Doesn't have to be T, that could be term 0, it could be the cost at time 0, it could be the price at time 0. We use a whole variety of different letters. That makes this one here T1, or C1, or P1, etc. Confusingly enough, T1 is the second term. Think of the numbers, these numbers down here, as the number of jumps in the domino sets, the number of times we've jumped. 1 means we've jumped once. We've started from 0 jumps at the 2, we've jumped once. And etc. all the way out to, well, that's T3, or T3 would be there, etc. to T, n take 1, Tn, Tn plus 1. Right. Now, here, we're going up by a constant amount. That constant amount is called the common difference. Clearly, our common difference here is 3, because we're increasing by a positive 3 each time. If you want to find, say, the algebraic way of calculating the common difference, you would do Tn plus 1 take Tn, and that will be equal to d, the common difference. Now, that looks like scary terminology, but what we're really just saying is take one step in the dominoes, subtract the one before it, and that will give you the common difference. For example, we could do 14, take 11, that gives us the 3. Note, if the sequence is going down, then the common difference would be negative. Alright, now, we use this terminology to describe patterns, and something that describes a pattern is called a recurrence relation. Now, a recurrence relation has 2 parts. It has a fixed value in the series, normally the starting value. So in our case above, T0 was equal to 2. And then there is a rule for linking 2 consecutive terms. And the rule for linking 2 consecutive terms typically looks like this. Tn plus 1 is equal to, in our case, Tn plus 2. Plus 3, because the common difference is 3. Sorry. What this is saying is, in order to get to the next term in the series, the next one, we go to the previous one and add 3, or add the common difference. So, let me just repeat. A recurrence relation has 2 parts. You need this one, a T0, then comma, and then a rule linking the next. Now go back, rewind the last minute, so you've heard the 2 parts bit twice, then twice again, and I'm going to say it a 5th time for you. It needs 2 parts. My class last year traumatized me by not including this bit here. That is very easy to leave out. I think they got so excited that they worked out, oh, there's a difference of plus 3, they forgot the initial term. Please don't. Alright, so let's write some recurrence relations to describe these sequences. Here, we're looking for a starting point. So our initial value, initial term, I'm going to use V0, is equal to 45. Then we need a rule of linking one to the next. Well, how do we get to the next? Here, well, we're subtracting 4. So I will get to the next term by taking the previous term and subtracting 4. Easy enough, that's the recurrence relation. This one here. Well, our initial term, or careful, if you used V, you must continue using V up above. If our initial term is 2, then we get from 1 to the next, we get to Tn plus 1 by doing 2 lots of Tn. And typically in maths, we would ignore the multiply sign and just write 2tn. Next one should almost be default by now. That first bit just has to be there. Then we get to the next one by taking the previous one and multiplying it by -2. 1 times -2 is -2, -2 times -2 is +4, etc. Now the last one's a little harder. You may want to pause, have a think about what could possibly produce it. You certainly know that t0 is 1. And then it turns out the rule for doing this, to get to the next stage, we do 3 times the previous stage plus 1. So to get from 1 to 4, we do 3 times 1, which is 3, plus 1 is 4. 3 times 4 is 12, plus 1 is 13, etc. So a rule like this, and you can see how we're going to make them more complex, can be used to describe quite a difficult pattern. Alright, find the 9th term in the sequence above using technology. Now, doing this by hand all the way out to the T8, or the 9th term, would be a little frustrating. So, what we do is we go to our calculator. And, there's one I did earlier. Let's go to a new one. Alright, and we get up a spreadsheet like this. Now in this cell here, we put our starting value, which is 1. And then here, we want to put in the recurrence relation, which will get us from 1 to the next. So our recurrence relation starts with an equals, and then we did 3 times the term before. In this case, the term before is A1. And then we added 1. So our rule, remembering, was this one here. And that's what we're putting in 3 times the term before, which is the cell above, plus 1. So here, 3 times that plus 1, enter. 4. And then we can click and drag down. And now we want to find the 9th term above. So the 9th term will be that one there. 9,841. Not so bad. Right. Now, they can also ask you to generate these by hand. Oh, and I should note that in the calculator there is another way called sequence generator, which we may have a look at later, but I really do like the spreadsheet because you can see it all laid out. Alright, by hand, you should be able to show all working. A0 equals -7. If we want the first 5 terms, and they can ask you to do this in the exam by hand, you'll need to do A1 is equal to 2 times -7 plus 1, which is equal to -13. A2 is equal to 2 times -13 plus 1 is equal to -25, and so on down. Alright, and that is all for now. Thank you very much. Stop recording.